Hello, everyone, and welcome to 15.8 as we upgrade polar coordinates into triple integrals and we make cylindrical integrals. Now, we've already talked a little bit about cylindrical integrals kind of back. It was around in chapter 13 or so when we kind of brought these up in the original change of coordinates and all that sort of stuff. Now we're going to start to actually integrate into cylindrical coordinates. And so if you need any sort of refresher about what cylindrical coordinates are, right, I recommend that you kind of go back around chapter 13 or so when we first introduced these sorts of things. In this video right here, we're going to kind of progress a little bit beyond just kind of sketching particular points and stuff like this. We're going to learn how to sketch cylindrical pictures in the RZ half plane. We will calculate the Jacobian for cylindrical transformations, and we'll get a little bit of practice actually evaluating out a triple integral in cylindrical coordinates. So that's our main goals for here. Okay, to get started, I'd like to go ahead and sketch z equals r and z equals 4 minus r squared in the RZ half plane. So the RZ half plane, that's a little bit of an interesting thing here. But you can imagine the z's going up and down sort of deal, kind of, like the classic X, Y, Z space. And the X's and Y's, right, because we only allow for a positive R value, positive radius, right, that's why it's a half plane rather than an entire plane, right? If we allowed for negative radiuses as well, right, you would get the negative half, but we're only going to allow for a half plane because we only have positive radiuses. And so, okay, if I was to go ahead and sketch z equals r, well, we can see that our independent variable is r and our dependent variable is z. Maybe I'll go ahead and use some different colors here, z equals r. And we'll go ahead and this is a nice straight line. It has an intercept of 0 and a slope of 1. It's kind of like the classic y equals mx plus b sort of deal. But in this case, right, we have our dependent variable is z and our independent variable is r. So we have z equals r is the same thing as z equals 1r plus 0. So again, an intercept of 0 and a slope of 1. It's a nice straight line. And again, it's only the half plane, right? Because we only allow for positive radiuses. If we allowed for negative radiuses, it would also contain, well, the negative half there. Okay, and let's also sketch z equals 4 minus r squared. So z equals 4 minus r squared. This is going to be a parabola. Of course, it's been shifted up by a factor of 4, and it's been reflected across the r axis, right? So it's actually opening downward. So it looks something like this. This z equals 4 minus r squared. And of course, you could sketch this in careful detail, right? And plot particular points and all that sort of stuff. But I'm just going to go ahead and sketch rather loosely here and just do the z equals 4 minus r squared and kind of what it generally looks like. So this is what it looks like in the RZ half plane. So if I would like to go ahead and take this and sketch these same pictures into space. So that is, we have X, Y, Z space. Then because neither one of these depends on theta, you can imagine that we can allow theta to run free, kind of similarly back when, if I was to graph y equals 4 back in our algebra days, and it was allowing x to run free, right? It runs left and right, and there is no restrictions on x, so it can be anything that it wants to be. And likewise here for theta, right? There is no restrictions on theta, so it can be anything that it wants to be. So you can imagine this, for instance, the z equals r sort of deal, this nice straight line, but we can allow it to be, right, any theta that it wants to be. And remember, theta kind of runs around the z-axis. It rotates these lines around the z-axis. And so you get this sort of cone-looking picture. And of course, right, if we were to go ahead and spend some time, right, z equals r is the same thing as z equals the square root of x squared plus y squared. Or that is z equals, and if we were to square both sides, we would get x squared plus y squared equals z squared, right? This is exactly the cone. Because it only has, right, the positive square root here, it's only the top half of the cone. But again, kind of the fundamental thing back to our quadric surfaces in 12.6, this right here is a cone. And so we ought to get a picture of a cone, and I'm quite happy, right? That kind of when we take this nice line and we spin it around the z-axis, right? We get the shape that turns out to look like a cone. And we could even draw maybe the top one up here. Again, it kind of continues on forever sort of deal in the positive z direction, but I'll just go ahead and draw the sketch on top. Now, likewise, if we were to go ahead and take this 4 minus r squared, right? 4 minus r squared, again, this kind of looks something like this. And if we were to take that and spin it around the z-axis, because again, it doesn't have any thetas in it. There are no restrictions on theta. So if I was to take this and to kind of just spin it around the z-axis, we're going to get a whole bunch of, circles and whatnot, right? The spinning around the z-axis. And this right here, if we had to guess what shape this was, probably an elliptical paraboloid comes to mind, right? So we see kind of these ellipses as cross sections. If we hold z constant and, kind of we have these paraboloids, this parabola sort of deal that, of course, we feel from the z equals 4 minus r squared. And of course, if we were to spend some time and to rewrite this into Cartesian coordinates, instead of r squared, right, it would be x squared plus y squared. And so that would be z equals 4 minus x squared minus y squared once we distributed that negative, right? And so again, this is an elliptical paraboloid. It's been shifted up 4 in the positive z direction, and then it's been reflected here. And so you get a picture that looks like this. So this is how we can actually sketch rather quickly, in particular, these cylindrical coordinates with z's and r's and sort of deal. Usually what I do, right, if I was to sketch this thinking ahead when we're doing triple integrals, I usually start off with a picture like this, and I quite literally think about spinning it around the z-axis. So I would do something like this. And I would also do the same thing with our elliptical paraboloid, so something like that. And quite often we're interested where these things intersect, and so you can see I kind of drawing their intersections here. But you can see that you can get a relatively fast picture in cylindrical coordinates, right? Very useful in cylindrical coordinates, just by graphing this in the RZ half plane and then spinning it around the Z axis. So this ends up being quite a useful technique to visualize what we have here. And just as kind of, I've kind of alluded to this several times, but I really want to emphasize, right? Using a sketch in the RZ half plane to sketch in space works if your surface does not depend on theta, right? You need to have this freedom with respect to theta so that you can spin it around freely. And so you do have to be careful if your surfaces do rely on theta. Be careful with this. In general, it will not work. Okay. And we'll see in class many times, right, how we can go ahead and use this. Let's go ahead and continue, though. And I'd like to calculate out the Jacobian for cylindrical transformations. So when we want to transform from Cartesian coordinates into cylindrical coordinates, right, in particular to integrate, right, we know that we need to calculate out this Jacobian for the integration factor. And so again, kind of remember here, if you wanted to go ahead and calculate this out, you need to calculate out the Jacobian of, and our coordinates in Cartesian are x's, y's, and z's. And we need to calculate out these derivatives with respect to r, theta, and of course, z. And then remember that we need to take the absolute value of this. And so, okay, we'll get to that here in just 1 second. So just as kind of a quick refresher before we jump into this, right? In cylindrical coordinates, x is equal to r cosine theta, y is equal to r sine theta, and z is just equal to itself, z. We have z coordinates in cylindrical coordinates. Okay, so let's go ahead and calculate this stuff out. We can imagine, right, we have the partial derivative of x with respect to r, the partial derivative of x with respect to theta, and the partial derivative of x with respect to z. Oops. Then we have the partial derivative of y with respect to r, y with respect to theta, and y with respect to z. And then finally, z with respect to r, z with respect to theta, and z with respect to itself, z. And so remember, we need to take the determinant of this matrix, and then we'll take the absolute value of this. Okay, so let's go ahead and calculate out if we take the derivative of our x transformation with respect to r. So again, I'm kind of looking down here, and if I was to take the derivative of x, this transformation with respect to r, so I'm looking at this one right here. If I take the derivative with respect to r, I'm just going to have cosine of theta left. If I take the derivative of x with respect to theta, I'm going to have negative r sine of theta. And if I take the derivative of x with respect to z, well, I don't see any z's in there, so that's constant with respect to z, and I'm going to have 0. Next up, the partial of y with respect to r is going to be sine theta. The partial of y with respect to theta is going to be r cosine theta. And the partial derivative of y with respect to z is going to be 0. And again, for all of those, I was looking at my y transformation. And then finally, for my z transformation, rather boring, the partial derivative of z with respect to r, well, there aren't any r's, there aren't any thetas, and there's exactly one z. So if I take the partial derivative of z with respect to z, I get 1. And so we get something like this. Now let's go ahead and take the determinant of this. Well, this one's a little bit funny because we're used to kind of having these matrices. We've been doing them for a long time where we have I, J, K across the top, right? And yet for this one, right, we're going to have stuff with cosine of theta, right? That's the first bit here. And then minus stuff with negative r sine of theta, right? It's because we don't have the i's, j's, k's along the top here. And then finally, we're going to have stuff with 0. Oh, that's going to be quite nice, right? 0 times anything is going to be 0. So you do have to be a little bit careful here. We do need to work across our first row here. And if you don't have i's, j's, k's, right, you do have to be careful and make sure you input whatever you do have here. So let's be careful. We're going to go ahead and cross out the first row and first column. And when I go ahead and I take the determinant of this matrix minor, we're going to have r cosine of theta minus 0. When I do the first row and second column, right? Well, that's going to be sine of theta minus 0. And finally, I don't really care so much here because I'm multiplying by 0, but okay, if I go ahead and I cross off that first row and third column, I'm going to have 0 minus 0. So that's like, okay, 0 times 0. Okay. Well, that's going to be the absolute value of r cosine squared theta minus a negative. That's going to be plus r sine squared theta. And if I go ahead and I factor out the sine squared, if I factor out the r from both of these, I'm going to have cosine squared plus sine squared. And so, of course, cosine squared plus sine squared is going to be the same thing as 1. Because we're only allowing for positive radiuses, positive r's, right? The absolute value isn't going to be doing a whole lot. And our Jacobian, right, for a cylindrical transformation is maybe not surprising here. It's just r. It's the same thing as if we had a polar transformation. And after all, cylindrical transformations are an upgrade of polar transformations just into, three-dimensional coordinate system where z is itself. And so maybe this isn't so surprising. Moving forward though, right, if you want to go ahead and transform from your Cartesian z's, y's, x's into cylindrical z's, r's, and thetas, well, of course, you're going to need to transform your coordinates, right? Using our transformation equations, x equals r cosine theta, y equals r sine theta, z equals z sort of deal. So that way your independent variables are r's, thetas, and z's. And then that integration factor or the Jacobian, right, that you need to make sure to include here is going to be, well, exactly as we calculated it up here, right? It's just going to be R. Okay. And then the last thing that I wanted to do, right, we've kind of touched base on the first two objectives here. We've sketched in cylindrical coordinates, from the RZ half plane. We've calculated out the Jacobian of cylindrical coordinates. And then finally, let's get a little bit of practice. We had this problem back from 15.7, calculating out the volume of the wedge cut from a cylinder by the planes z equals negative y and z equals 0. And now I'd like to go ahead and do this using cylindrical coordinates. So again, the first thing that I recommend anytime that you are doing some integration problem is that you get a good sketch, kind of an idea of what's going on here. And so let me go ahead and sketch here. X squared plus y squared equals 1. In fact, let me go ahead. I'll sketch this one in blue. X squared plus y squared equals 1 is, of course, our nice circle in the xy plane. So if I was just in the xy plane, this would be a circle of radius 1. Notice, however, that it doesn't have any z coordinates, right? And that's why it says it's a cylinder, right? And so we can go ahead and run free with respect to z. And you get this nice kind of toilet paper roll or what have you there. That's takes that circle and kind of moves it freely in the z direction. Now, moving on, if I was to do z equals 0, z equals 0 is, of course, the same thing as the xy plane. So not very exciting there. So that's just kind of, if we were to kind of intersect the two, z equals 0 is just going to be the xy plane. And maybe if we're interested in the piece that's kind of interacting with this x squared plus y squared equals 1, it's going to be the piece that kind of deals with inside of this cylinder here. And then finally, z equals negative y. Z equals negative y. So you can kind of think about this is going to be a straight line with a slope of negative 1 in the y direction. So that is, if I was to go over, for instance, 1 in the y direction, right? So this is a y value of 1. According to this plane here, z equals negative y, the z value would be down by 1. So something down here. And so you get this kind of nice straight line, again, with a slope of negative 1 in the y direction. And likewise, you can kind of go up in this direction here. If y was equal to negative 1, kind of back here, then you would have negative 1, right? Z would be equal to positive 1. And so we've already sketched this a few times, but if you kind of take this and do this slantiness sort of deal, and let me go ahead, I'll shade this maybe in purple just to kind of stay consistent. We get a nice wedge that looks something like this. So we're going to find the volume of this wedge that's above the xy plane, or z equals 0. So again, maybe let me go ahead and shade this in green here. So between this z equals 0 and z equals negative y, and inside of the cylinder, x squared plus y squared equals 1. And so, by the way, notice that I went right into sketching this in the x, y, z space rather than doing the RZ half plane. The RZ half plane is great for many pictures. But in this case, right, if we were to go ahead and sketch this or kind of transform this into cylindrical coordinates, we would have y is the same thing as r sine of theta. And because this depends on thetas here, remember, this will not be a good candidate for sketching in the RZ half plane, right? So using a sketch in the RZ half plane to sketch in space only works if your surface does not depend on theta. So that's why this one, if you were to try to go ahead and use this, and I recommend it's a good idea to try it out, right? And see that you don't actually get the right picture here. Okay, well, with that, if I was to go ahead and try to calculate out this volume, that is, we need a triple integral here. We can think a little bit about, right, if I want to calculate out the volume from this wedge, we're going to be integrating with respect to 1, with respect, right? The function here is going to be 1 in order to get the volume. And if I was to go ahead and think about the order of integration, and again, I'm going to integrate this in terms of cylindrical coordinates. That is, well, I'm going to need an r dz, dr, d theta. So that's exactly from this theorem up here, right? Whenever you do this transformation into cylindrical coordinates, we need to have this extra r bit, this integration factor, this Jacobian, right? Along with our dz, dr, d theta. Now, of course, 1 in Cartesian, if I was to go ahead and transform this into cylindrical, it's the exact same, right? But normally, if you had x's, y's, or z's, right, you would go ahead and do that transformation. And so that you would no longer write x's, y's sort of deal. You would write them in their polar or cylindrical equivalent. All right, so this is what I have so far. Now, of course, the big thing is that I need to set up my bounds for this. What should be my bounds of my integration? Well, if I'm integrating with respect to z first, imagine that I'm traveling in this z direction, and I have to think about what do I hit first to enter into the solid, and what do I hit second, right? How do I exit the solid? Well, it seems like if I'm traveling in this z direction, the first thing that I hit is this green surface, right? This green surface is how I enter into the solid, and the purple surface is how I exit the solid. So, of course, the green surface had z equals 0, and the purple surface had z equals negative y. So if I was to go ahead and set this up, we would have, we enter in through z equals 0, and we exit through z equals negative y. Now remember, negative y is not legitimate as far as cylindrical coordinates are concerned. So we do need to go ahead and transform this with respect to r's and thetas. And so, of course, according to our transformation equations, y is the same thing as r sine theta. And so we can go ahead and everywhere we see a y, we're going to go ahead and put r sine theta. Okay, next up, kind of very similar to when we were doing this in 15.7, we need to go ahead and take this and maybe smash it into the xy plane. This is what I would really recommend. So again, pretending that there are no more z's. After you integrate with respect to z, z's are gone. And so if I was to take this kind of picture and smash it down into the xy plane, we would get a picture that looks like this. And again, I'll shade it in green here, but you could also shade it in purple or what have you. So notice that we have the x's on both the positive side over here and the negative side, all the way from x equals positive 1 to x equals negative 1, right here. The y's, on the other hand, go from 0 down to negative 1, right? There aren't any y's in the positive direction. And so again, kind of here, we have x's that go from negative 1 to positive 1, and we have y's that go down to negative 1, but we don't have any of the positive y's. And again, I'm trying to describe this with respect to r and with respect to theta. So this lives inside of a circle here, right? Inside of this in 3 dimensions, it's a cylinder, this x squared plus y squared equals 1. And of course, that's the same thing as r squared equals 1. And if we stick down to positive r values, that's r equals 1. And so we can see as we kind of go outwards here, emanating from the origin, like r's do, we see that as soon as you take the tiniest step away from the origin, you are in the region that you're supposed to be integrating over. And the way that you stop this, right, is that you go through the circle of radius 1. So that is, our r's range from 0 to 1. As soon as we take the tiniest step off of the origin, r equals 0, we are in the region of integration. And as soon as we exit through radius 1, that is x squared plus y squared equals 1, that cylinder in 3D, right? We have exited our region of integration. Finally, we need to think about our thetas, right? What should our thetas be in order to encompass just the bottom half of the circle? So remember, thetas start off with the positive x-axis, and they rotate counterclockwise. So you can see that we actually enter into our region at theta equals pi. and we stop at theta equals 2 pi. That's where we would end. With this, we have successfully set up our integration, our triple integral here, and I find that this is quite often the most difficult thing. However, let's go ahead and see this one all the way through. Let's evaluate it out and see that we get the same answer that we did actually when we did this in 7.3. So let's finish this up maybe a little bit faster now that we've done the difficult bit. So when I go ahead and I integrate with respect to z, well, r is constant with respect to z. So when I integrate with respect to z, I just get a z. And we do this from 0 to negative r sine of theta. And we still have to integrate with respect to r and with respect to theta. So let's go ahead and plug these things in. When I go ahead and plug in 0 and I plug in this negative r sine of theta, right, we're going to have, well, negative r sine of theta minus 0, which doesn't really do a whole lot. And there we go. Now let's go ahead and integrate with respect to r. So when I integrate with respect to r, well, let's see, we have a negative sine of theta. It's going to be constant. Doesn't really depend on r at all. And notice that I have an r and an extra r, right? So that's r squared. And so if I integrate that, I'm going to have a 1/3 r cubed. And this I need to evaluate from 0 to 1. And so, of course, if I plug in 0, I get out 0. And if I plug in 1, well, I get 1 cubed, which happens to be 1. And so, okay, well, 1 cubed minus 0, that's just going to be 1 here. So in fact, you could kind of just drop that all together. Lastly, if I was to integrate with respect to theta, so I have this negative 1/3 that's along for the ride here. And when I integrate sine, I get negative cosine. I need to evaluate from pi to 2 pi. Let's see, negative and a negative. So that's going to be positive 1/3. And when I plug in 2 pi into cosine, I'm going to get 1. And I need to subtract away when I plug in pi. Cosine of pi is going to be negative 1. So minus a negative 1. Well, that's the same thing as plus 1. And so I get a final answer of 2/3. Lo and behold, the exact same answer that we got back in 15.7. So we can see that including this extra r here was exactly the thing to do in order for our transformation to work out correctly and for us to get the correct answer for the volume here. All right, with that, this is where we will end it for this video. I hope that you guys learned something. Again, we will be expanding on this significantly more in class, so please bring any questions that you may have to class. I will see you then. Thank you so much, guys.